For coming down. I think for those of you who don't know me, my name is Jamie. I'm a master's student and Amit is one of my supervisors. So over the past 2 years, we've undertaken quite an interesting project that works in the Southern Ocean of Antarctica. And in this presentation, I'm just going to show to you basically what we've been working on, as well as some preliminary data from the region. So this device is called SHARC Buoy. It's a low-cost multi-sensing platform, which has been created in collaboration with the UCT Oceanography Department. Now, UCT has a big research interest in the Southern Ocean because the dynamics in the region affect the weather in Cape Town. And also, we are one of 22 countries who has unlimited access to the continent as well as a research base. So because of this, we do perform a lot of experiments there. And that brings me to this presentation. So I'll start off by giving a background to what we're talking about. I'll then go through the system, and I'll also give you guys a taste of what you can expect in your honors years and if you decide to, your master's years. And just show you how we tested it, talk about some of the results, and then at the end, I'll take some questions. Cool. So remote sensing is basically taking an autonomous machine or a device, putting it down in an area and being able to access it from another location without wires. Remote sensing is very critical to Antarctic science because in the region, there is a fundamental lack of infrastructure. There's no power stations, there's no permanent bases, there's no wireless connectivity. So in order to reach some of the harder places to gather data, you need remote sensing. This has typically been done by satellites, but over the recent years, there's been a boom in what is called in situ autonomous devices, or devices that you can place in the region, such as those shown to the right. These typical devices consist of an array of sensors, a processor, as well as a portable power supply and some form of communication. This is typically done using satellite networks because they have the widest coverage of all the methods. They're also the most supported. So you'll find that a lot of these devices will use either one or two satellite networks, specifically Iridium. The problem with the current state of technology is that it is extremely expensive. There's a buoy called Swift Buoy, which is E in the bottom corner. That cost 500,000 Rand for a single device. And even the cheaper ones are no better. There's one called Trident, which is H. That one costs about, I think, 5,000 pounds. And the one C, this was a unique buoy that cost about close to 1 million to 2 million Rand. But also a problem with these devices is that they are very specialized. So they've only got a certain number of sensors, or they've been built for a specific purpose. And because of this, you can't, if you have different research objectives, you have to buy different systems, and it makes it difficult to collect data on a wider area. That being said, we started the project so we can combat this by creating a scalable, low-cost, multi-sensing platform capturing as much information as we can about the region. And if it's low cost and survives for a long time, we're able to expand the network across the region and basically cover a larger area and be able to populate the data sets with higher resolution data. So with this in mind, we move forward to our research objectives, and that was to prototype and build a low-cost system, deploy it in the Southern Ocean and get results, verify the test and survival time, verify the sensor performance, and generate preliminary data sets. As you can see, these are quite simple research objectives, and that's because we optimized, or we started the project as more of an investigation into what is possible. While the oceanography department has spent many years in the Southern Ocean, this is the electrical engineering department's first venture. So we wanted to gain an understanding of the region and how the device would hold up. So we get to the design methodology. The very first step we took was deciding what were our key measurement variables. And we decided, well, we honed in on the conditions surrounding sea ice formation and looking into other phenomenons in an area called the marginal ice zone. The marginal ice zone is an area that surrounds the Antarctic continent, where the ice that forms does not fully consolidate. And because of this, you experience some interesting phenomena, such as ice flows drifting for hundreds of kilometers over the winter months, as well as giant waves, 7 meters tall, propagating throughout the region for kilometers in. In order to understand where these phenomena come from, how it affects the region around it, we need to measure ice drift, environmental formation conditions, as well as measure 6 axes of inertia, so we can gain an understanding of the dynamics of the sea ice as it interacts with waves. The environmental conditions are more for the formation of the ice flows and understand how big they can form, how they form into the shapes that they do, and how the temperature, pressure, and even the wind speed and direction affect the formation cycle over a seasonal period. To measure ice drift, we put in a GPS. We also wanted to measure the error associated with those GPS measurements in order to verify how accurate they were. Finally, to gain insight into the buoy, we needed to measure the status as well as the battery life. And that brings us to our first iteration. This is SHARC Buoy version 1. And we built this system for the 2019 Southern Ocean expedition called the Scale Winter Cruise. This was the first in the series of buoys where we were trying to establish how the electronics were going to operate in the region, as well as how long we can expect it to last. So we went for a more simple approach. We used a STM32 microcontroller, which is a bit different to the one that you guys have used in your embedded systems course. This is the F4, and it comes on its own pre-built development board. There's also an Iridium modem. That's the device with the antenna, as well as a GPS, which is on the top right-hand corner. The device was powered by C-cell batteries, and the mechanical enclosure consists of a temperature-resistant plastic. And as you can see in this photo, you can see the base plate. There's a lid that goes over, and that forms the top enclosure, and the bottom enclosure is where the power electronics are stored. After the expedition, we moved on to version 2.0, which was featured more advanced sensors, a more robust, optimized set of firmware, increased memory, as well as a more robust mechanical design. If I go back to the buoy in version 1, you can see that it's a single PCB. We found that this caused some issues that I'll explain later on, but it wasn't mechanically secure. This configuration allowed for us to prototype and in a mechanically robust way, while being resistant to what we can expect in the region. We split it into 3 boards, each board serving a purpose. So on the top, you've got your communication module. The middle, you've got your storage and your microcontroller, and the bottom, your sensors. The microcontroller is the STM32L4, which is lower powered, hence the L. So For our first deployment, we took 6 buoys along, and due to time constraints, we only managed to deploy 3. We deployed 2 in the in marginal ice zones 1 and 2, and these deployment locations can be seen in the figure at the bottom. The marginal ice zone is split into 3 areas, where each area has more consolidated ice. We started off in order to deploy the system, we had to carry the buoy in a basket with 3 other crew members and be lowered onto the about a meter above the surface of the ocean, where we selected a suitable ice floe and dropped it. Unfortunately, during the deployment, we encountered some issues, the first one being a power systems failure during the first deployment. This was because the configuration we used, we used a switch mode power supply, which ended up malfunctioning when we got to lower latitudes. And we attribute this to a stability issue. If you think about it, a switch mode power supply is a control loop. And we weren't sure at the time, but something was throwing the control loop off. We later realized that it was the internal resistance of the batteries we used. After fixing it, bypassing the power supply and coming up with a solution, we deployed again a few days later, but this buoy also failed. We are still not quite sure why it failed, but we can attribute it to a rougher than normal deployment, which may have resulted in mechanical failure. Finally, we deployed a buoy at the back of the ship, where it lasted 7.5 days on a single battery charge, and it successfully transmitted data through the Iridium network. And the data can be seen in the figures in the slide. To the left, we have a temperature comparison, and to the right, we have a GPS trajectory plot. As you can see, there will be some gaps in the data, and this can be attributed to 2 sources. One is the failure of the Iridium modem to transmit data packets. And this happened when we encountered storms or unusually large cloud cover. We also took the buoy down after 7 days to change the battery, and as a result, you'll see a gap. But after we got it back up and running, it transmitted perfectly. The GPS worked perfectly. However, the temperature plot, as you can see, does not correlate entirely to what was measured on the ship. Further calibrations, as well as further calibrations, are required to bring it in line, but we can attribute this failure to the possibility of moisture or just data corruption that occurred while the buoy was sampling. For version 2, we experienced better readings, better findings. The first deployment of this version happened on the mainland of Antarctica at the South African Antarctic base called Sanai 4. Here it was deployed on the guardrail above the base, and as you can see, the GPS coordinates on a high scale show a close match to where the base is, but if we zoom in, we can see that it's offset by about 15 meters. In order to account for this, once again, we'll need further calibrations. However, what is promising is that most of the sample points fall within 1 standard deviation of the mean position, and that's shown in blue. If we move on, we can see some more data that we collected, which is temperature to the left, pressure to the right. I know that these graphs look like they are the flipped versions of the other, but I can assure you this is because of the nature of the sensor. We used a BMP temperature and pressure sensor, and the pressure compensation measurement, or the pressure measurement, is dependent on the temperature, hence the fluctuations. Finally, to get some dynamic data, we deployed the version 2 in the marginal ice zone using the RV Polar Stone in 2021. And the plot to the right shows an ice flow drifting through the Southern Ocean from, I think, 29.6 degrees west to about 31 degrees west. What's interesting to note is you see some changes in trajectory as you move towards the 31 west, starting from where it started at 29. And what was observed during the cruise is that the ice flow that we put it on broke apart. And this could be the result of collisions and further breaking up of the ice flow. Finally, the temperature and pressure plots for two deployments look like this. Oh, I should mention that we brought two buoys along on this expedition, but one of them failed to lock onto the satellite network, so we were unable to receive any GPS measurements. But we still got temperature and pressure measurements, so this is what they look like. Once again, you can see some temperature dependence, but the data looks a lot better. So where to from here? Well, much like the university is always looking to innovate and improve, and so are we. We're moving into different phase in the development cycle, and we're going to shrink down the electronics and make them more robust. With this data, we're able to calibrate our sensors more effectively and gain more accurate data. And there are more interesting things to work on, such as inter-buoy communication, using something called LoRa, as well as additional autonomous functionality, more firmware design, or even just more sensor development. So that's the presentation. I'd like to thank you guys for listening. Hope I didn't speak too long. I'd also just like to acknowledge the work and contributions to the project. You can find these in the slides, and I'll now take any questions. Yeah, Theodore.
Hi, how's it? Thanks for the presentation. I don't know, this may be a silly question, but how far would you normally let the buoy travel? Would you let it travel all the way, or how long is the distance? 7 days? Does it go all the way from Antarctica to South Africa, like the tip, or yeah, I'm just trying to conceptualize it.
No, that's a very good question. So I think you're talking about the ship deployment.
Yeah, correct.
Yeah, so on that path, it's kind of an interesting one. So the actual trip from Cape Town to Antarctica took about 5 to 7 days. But on the way back, we kind of stopped a lot so other groups could do their research. So essentially what that is showing is 14 days worth of deployment from where we started in the marginal ice zone all the way to East London, where we finished.
Okay, I see. And obviously along the way, the ice would eventually break up or melt or whatever. How would I mean? Is the buoy? Yeah, the buoy is definitely waterproof, but I mean, is there any useful information after the buoy sort of like falls into the ocean after the ice melts, or?
So I'd just also like to clarify, this was deployed on the ship. This data came from the buoy on the ship, but there is very useful information that we can extract from this GPS. So even though it wasn't ice related, as you can see there, I drew some yellow circles around the dots. And that's an indicator of something called the dilution of precision, which measures how inaccurate the GPS signal is. I'm not sure if you guys have, ever sent a live location and you noticed on your phone how it says accurate to 5 meters or accurate to 25 meters or even more. The bigger the dilution of precision, the more inaccurate that measurement becomes. So as we can see below 52 degrees, we get more inaccurate measurements than if we were above that and that's kind of due to the satellite spread. That's quite useful, so it gives us an understanding of what to expect.
Okay, I see. Thank you.
Sure.
Actually,